Good morning, good afternoon, good evening. My name is Louis. I'm from Boston College, and this is a joint work with my postdoc Dimitris and Nitin Vaidya from Georgetown. So the paper is about asynchronous Byzantine approximate consensus in directed networks. And so here, just let me remind you on the definition for consensus. You have n nodes, and each of them have a real value input. And when we say an algorithm, consensus algorithm is correct if it satisfies three conditions. Termination, meaning that everybody needs to produce some output eventually. And agreement, meaning that everybody needs to agree on identical or the same output. And the validity, meaning that output must be some input. And the model we are considering is that we have n nodes and up to f nodes may be Byzantine. And we consider the case in the message passing system, and it's a typical asynchronous setup. And the new thing is that the communication graph may be partially connected. And because of the FLP impossibility result, then we know that it's impossible to solve an exact consensus in this case. So we have to aim for the approximate consensus case. So what's approximate consensus? The setup is the same for the first part. You have a real value input, and then you need to satisfy termination. And now we relax on the agreement, meaning that we only agree on roughly the same output for the four free nodes. And then the validity is also relaxed because now we only require the output in the convex hull of a four free inputs. So we still need to satisfy termination, agreement, and validity. But both agreements and validity are relaxed. And here's some illustration, like typically in this kind of algorithm, each node will have some state, and then eventually the state will become the output. And then because we have a Byzantine node, we cannot control what they want to do. So we are only interested in the states or the final decisions of four free nodes. And then suppose here's a real time, and then this is the value of the each node's state. And then at some point of time, the correct node or the four free node, they will decide an output, where output is the state at that point of time. And then they don't need to agree on or output exactly the same thing. And then because of asynchronous, they may not output on the at the same time. But all we require is that when I or j output something, then the value of these two for any pair of four free nodes must be bounded by epsilon, where epsilon is some constant specified by the correctness condition. And then Byzantine approximate consensus in the clique has been well studied. And then the first one is that this famous FLP result. We know that if we want to tolerate failure, and then there's a asynchrony, then we know that it's impossible to achieve. And then after that, then at the left, they come up with a solution so that actually in the asynchronous system, we can achieve use iterative algorithm to solve approximate consensus, but like n has to be greater than or equal to 5f plus 1. And then after almost like 20 years, then we have this AAD paper in Opodis. Basically said, no, why do we need to use iterative algorithm? We can use something like more fancy. That's what we call like kind of generalized algorithm, and then have optimal resilience, meaning that they can solve approximate consensus using only 3f plus 1 nodes. And then the difference between the iterative and then generalized, the key is that in iterative algorithm, there's no message forwarding. But like for generalized algorithm, it's okay to forward message. And then that turns out to be the key. And in this work, we consider incomplete network, meaning that the network is only partially connected. Moreover, each link is directed link. Okay, so it's possible that I can talk to you, but I cannot hear from you. And then the first motivation is that large scale network is usually not a clique, so it's very interesting to study incomplete network. And then the directed link or directed channel is inspired by the kind of a wireless channel, because maybe I have a higher power, so I can shout louder so you can hear me, but like not the other way around. Okay, so that's the setup of our message and passing model. The network is partially connected, and then the link is directed. And here is our key research question: is that what is the tight, sufficient, and necessary condition on the underlying directed communication graph, so that we know we can solve Byzantine consensus in asynchronous systems? Okay, so we are interested in tight conditions in the directed network, and then we have Byzantine and asynchronous. And here are some of the prior result on like fault tolerance in incomplete network. So we divide the problem into a few different categories. So the first part is on the synchronous system, and here's a synchronous system. And then we also have an undirected incomplete network and directed incomplete network. And then for the crush one, and then synchronous or synchronous, actually is like pretty straightforward, implied by prior work. And then the key advance is by Lamport-Dolev, and then this Fisher-Lynch. And so, and then for the directed, like just like some recent result by us back in like 2015, and then we've identified the tight condition for all three cases, but not this one. And then finally, we have this work to close this problem. So now let me kind of show you that why directed case is much harder than undirected graph. So back in this 86 paper, what they essentially prove is that 2f+1 node disjoint path between each pair of nodes is both like necessary and sufficient. And then for sufficiency, it's that it's intuitive, because that once you have this 2f+1 kind of redundant path, you can do reliable communication between any pair of nodes. And then, for example, in this graph, you tolerate like one failure, because, for example, V2, if V2 want to send a message to V4, I just use this V2, V1, V4, V2, V3, V4, and V2, V5, V4. And then for B4, you can just it can just use a majority voting to figure out what the original message sent by B2, even if like some of them might be faulty. And if like B2 try to like send like kind of bogus value to each of them or mismatch message, and B4 can also identify that. And then in this paper, it has shown that this condition is also necessary. So in undirected graph, consensus is closely related to the feasibility of reliable communication. However, it's not the case for directed graph. So for example, because of the first observation, that's very simple, is that all pair reliable communication is not necessary, because I suppose you have A, it's a clique, then you can solve consensus here, then everybody inside B, suppose it has like 2f+1 link from like the nodes inside A, then you can just learn the decision from A, then you can solve the problem. So that's simple, but like you don't have all pair reliable communication. And in other words, you need to consider this kind of asymmetric information flow. So for example, like B knows that, okay, I have a different role from A. I just need to learn the decision from A, and then somehow A need to transmit message to decide among themselves. That's what we mean by asymmetric information flow. That's the first main challenge. And then the second main challenge is that we in our past work, we found out that in this kind of graph, here you have a top clique. So here V1 to V7, it's a clique inside, so denoted by K7. And then here on the bottom, it's also a clique. But the cool thing is that I only have like 2f directly links across the edges. So here from the top clique to bottom clique, I only have a V1 to W1, V2 to W2, V3 to W3, and V7 to W7, and also like vice versa. And what this implies is that you only have two F node-disjoint paths across top and bottom cliques. In other words, you don't know how to do reliable communication between U and Ws. And then that's the key thing that we need to address. Okay, so that's the why directed graph is much harder than undirected case. So before I present you the result, let me show you some definitions and conditions. So the first condition that we define is called the concept of rich set. So the notation reads like this: you have rich V and F is defined as the set of all nodes that's inside F bar, where F bar is equal to V minus F, and such that U has a directed path to V in the graph GF bar, meaning that the graph imposed by the node set V minus F. So now let's look at this illustration. So you have all these nodes, and then you have V here. And then what we mean by the F bar is that we remove F and then consider here only A, B, and B. And then any ones that has directed path to V is inside rich VF. And by the definition, V is also inside rich VF. But in this case, suppose B doesn't have any way connect to V, so the set B does not belong to rich VF. Okay, so that's the definition of rich set. And then based on the notion of rich set, we define the condition called 3 rich. So the condition is a bit long, but let me try to read with you. So the 3 rich condition is satisfied if for any nodes U and V inside our vertex set, and any node subset F, Fu, and Fb, such that all these 3 set is a mode size of F, and then we have a U that belongs to the complement of F union Fu, and V belongs to the complement of F union Fv. So here is a kind of a notion is that first I need to pick that 2 distinct node U and V, and then I pick a set F, so it's common for both U and V. And then for each V and U, I need to pick the FB. So in this case, for V, I pick FB. And then after I pick F and FB, I can figure out what's a rich V with respect to F union FV. So in this case, I suppose this blue one is a rich V F union FV. And then for U, I do the same thing, but the difference is that F is the same, but I need to pick another FU. Okay, then you can figure out what's a rich U and F union FU mean. So here just one special case. So in the sense that FU could be intersect with the blue nodes here, or FU could intersect with FV, but you get the idea. So now what's a 3 rich condition? 3 rich condition is that for any combination of the set and then the U and V that you pick, once you figure out what's rich V and rich U, the intersection must be non-empty. Okay, so that this blue set and then this blue set and then green set will intersect with at least one node. So high levelly, what does this mean? This means that for F, we want to capture the true 40 nodes. And for FB, it's kind of with respect to or from the perspective of node V, this FB might be slow or they might be the 40 nodes. So we also need to consider that. And similarly for FU. So what this condition try to capture is that even if we remove the influence of F, FU, and FB, we still share a good common source for any pair of good nodes U and V. And then that idea and that intuition will be the key for our correctness proof. But the challenge is that we don't know the identity of the such good common source, and because this FFU, FB could be arbitrary, then how do we address that? Okay, so now remember the condition for 3 reach, because that's our key result for this paper. And then actually that if you look at the paper, we can also define similarly for 1 reach and 2 reach. And then it turns out that our PODC 2015 paper, the condition state inside there can be transformed into 1 reach and 2 reach. And then this work, the contribution is to show that 3 reach is actually both necessary and sufficient to achieve Byzantine Approximate Consensus in asynchronous systems. Okay. And this result is quite interesting, because if you look at that, for crush failure, synchronous and asynchronous, the condition is different. It kind of means that asynchrony has worse result for crush. But if you look at the Byzantine, it's both 3 reach condition. So in a sense, you can say that Byzantine's kind of effect is that Byzantine's damage is more than asynchrony. Okay. So now let's focus on sufficiency. Why does it work, and what kind of algorithm can we have? And then the simple thing we try is that suppose for node V, I flood everything and on every possible path. So there are exponential number of paths, that's fine. I just want to figure out whether we can solve it. And then how do I know that I can start forwarding, or how do I know I collect enough I can use the value to do? So one idea is that, okay, now I want to identify the set FB such that the set size is at most F. And this set FB can be used to explain the faulty behavior or the missing message. So for example, if you see that, okay, some of the mismatch message that could be some source or some kind of relay nodes, then you try to remove that. Or if you didn't hear something, you can try to remove something. And then until you can figure out this FV, at the point that you can figure out this FV that explain all the inconsistency or all the missing message of all the message you have received from this run, then you can try to update using your own local state and all the message received from the reach V and FV. Okay. However, this algorithm does not work. It doesn't even work in the in a clique, meaning that in a complete graph. So here's a very simple example. Suppose you have 4 nodes, W, U, V, and X, and then let's define view as the set of message that each node has received. So suppose at this point that V receives 0, 1, 1, and then U receive 0, 0, 1, and then actually at this point nobody lies, so that V sees that, okay, everything is consistent, and then it could be the case that U has already crushed, so I should start at this point, and similarly for U. But it actually doesn't work. And then the reason is that for this kind of approximate consensus, one trick you usually do is that you need to discard the extreme values, because they could be from faulty nodes. So suppose F equal to 1 in this case, then you say that, okay, I see that X has 1, then it's possible that 1X is a faulty node, so I need to discard that. And it's possible that W is a faulty node, I need to discard that. So all this thing discarded, then the only thing that it's safe to agree on, or the safe to update my state, is 1. And similarly for U, 0. Then you can repeat this argument again and again, and you find out that V and U, they actually don't converge. So you don't have any agreement. And here, how do we address this? Is that we need to use a technique actually kind of inspired by AAD paper, is the idea of witness. So whenever you think that I have received enough message, I can identify this FV, then I need to act as a witness. I need to tell others that, hey, I have received this set of message. then once I heard that, then I need to collect all the possible witnesses and then waiting for some of the missing messages. And then once I get that, then I'm guaranteed that I use a receive message to update state, everything will work out. So here's how this kind of witness techniques works from the example I show you. So in this case, V is actually the witness of the message from W, V, and X, because that's when V stops updating or stop waiting for more messages. And suppose in this case, because V thinks that W, V, X are all for free, so it need to wait for their witness messages. And suppose that W has heard from you, then W will tell that V said that, hey, I have received use message, you should also wait for it. And then the design is that if you are correct, then you tell me that you have received some other people's message, then I'm guaranteed to receive that message. And so in this case, actually, V will be eventually receive use message. And then in this case, if you do this discard top and bottom thing, then if it turns out that V will use state to update the new state, and then by using the simple arithmetics computation, that this kind of common value that used to update new state is enough to prove convergence. Okay, so that's the full picture. We call it the algorithm Byzantine Witness, because at this key witness ideas are the core of our algorithm. So first we do this flood on every possible path, and then we do this kind of multi-threading. So for one thread, you need to check for each FB, because I try to identify what's the potential faulty set. And then the first one is I will wait until I can receive all possible message, excluding FB, because FB is my guess of the faulty set for this particular thread. If I succeed, I will try to send complete message, and MV where is all the message I have received so far at this point. So this is the witness part. And then again, I need to wait for all the possible witness, excluding FB, because I think that's what's the for free node in this particular execution. And then for each such a complete message there, I need to receive more message, because it's possible that you receive some more information than I did. So I need to learn that thing as well. And then once I find out such FB, so it's possible that my guess is wrong, so that this particular thread is never going to terminate. But like our algorithm is constructed in a way that I know that exactly one thread can proceed, and then we can use the message to update our new state, and then that's complete a phase. And then if we run for enough number of phases, it's guaranteed to satisfy the epsilon agreement. Okay, so now correctness, it's a bit subtle, but let me try to give you some very high level idea. So the first is that flooding works even if you lies about complete MU. And then this is not entirely obvious, because the challenge is that you might lie. And then how can you guarantee that you will receive something that you lied about? And because of the three rich condition, so there's enough redundancy so that the node V can either detect that you is lying, or it could receive the message that you told you to receive. Okay, so that's the first part. And then the second part is that for regarding the epsilon agreement, remember that the example we saw, we need to have used enough common information to update our future state so that we can argue for convergence. And then this enough common information need to be shared even after we discuss potential faulty values or potential kind of extreme values. And the way we do that, so first, let's see why that's not straightforward. So even for three rich condition, there's only guaranteed one good common source. So it's possible that you drop that both U and V drop that value, and then you don't have anything in common. And then that's where we have why this witness thing works, because common good source will add as a witness, and then you will need to receive kind of all the information this source told you so, and then that information turned out to be enough. And then after we drop those, and then enough information from the good source will never be discarded, so you will share common information, and then you can use a simple trick to prove for convergence. So let's correct this. First, we need to show flooding works, and then the next we need to show that there's enough common information. Okay, so finally, the consensus algorithm. First, we need to show termination. That's kind of liveness from property 1, meaning that the flooding actually works. You can receive all the information you want, and then you can actually identify 40 kind of nodes. If you cannot, that means that nobody really lies. And then the epsilon agreement, because everyone share enough common information, which is a property 2 I told you before. And then finally, there's a validity, and then that's ensured by our update rule that essentially is drop like kind of extreme values. It's a slightly generalization of prior work in this 1986 paper and then AAD paper. Okay, and then there are more technical details in the paper and then in technical reports. For example, we also identify another graph property that's slightly more complicated, but it's much more intuitive for arguing the property when we try to propagate messages. And then for our generalized update rule, that might be also useful if you consider this kind of incomplete graph, and of course the convergence proof. And we also have this necessity proof is based on this indistinguishability argument. Okay, to sum up, what we are doing here in this paper is we identify the tight condition for directed graph to solve Byzantine consensus in asynchronous system. And then we have like this 3-reach condition, and also this algorithm Byzantine Witness might be of interest. And then the list table is the key thing. Like for directed graph, we have this our prior work solve this 3 problem, and then in this work we solve a Byzantine approximate consensus in a synchronous system, and then this new kind of condition identified is very useful for this kind of approximate consensus. And 2 open problem that we are very interested is that 3-reach condition. If you remember, it's very complicated. You need to check all the possible set. So like, how do we check that efficiently? Oh, that's NP hard. We don't know. Yeah, and then right now the algorithm complexity is pretty bad because we basically flood on every possible path. And how to improve the time complexity, how to improve communication complexity is also like interesting problem. All right, that's all. Thank you.